Today we'll be modeling constant velocity. Constant velocity is when an object in motion has no acceleration, also known as change in velocity. The purpose of today's lab is to compare computational models and our observations of an object in constant motion. On a surface level, these models are good at predicting motion, but they're not always 100% accurate to the motions that we observe. We can predict the motion of an object in constant velocity using the formulas derived from Newton's second law, the position and velocity update formulas. We will use these formulas because the object we will observe will have no forces acting on it during the observation period, so long as we neglect friction. This means that the object will be in constant motion as its velocity will not change, because there's also no acceleration. For this experiment, our system will include a standard 500 milliliter water bottle rolling across the floor. After I push the water bottle, there will be no forces acting on it as it rolls to the right, allowing us to assume it's in constant motion, because the velocity shouldn't change because there are no forces acting on it during the time we're observing. After analyzing this footage in Tracker, we can use the observed velocity to create a model from Python code. This code will predict the position of the bottle by repeatedly using the formulas derived from Newton's second law to calculate the position in small steps in time. First, we will take a look at the code on the right. Here, I entered the bottle's position and initial velocity for the model to use, both of which were derived from Tracker. Delta t is the parameter that decides how far forward each iteration in time will go upon each calculation. The code on the left represents the calculations that will be repeated. Note that the vector representing the net force is 0. This is the key to constant motion. Each iteration of the while loop will calculate both the velocity update and the position update, and apply it to the next loop. After running the model, we can compare our observations made in the tracker and the model's output of the bottle's position after some time. The model predicted that the model would move at a perfect constant velocity, while the observed is a bit more variable than the models. Although they are not exactly the same, they are very close together, suggesting that the model is accurate. A possible explanation for the differences may be human error when tracking the position of the bottle during the observation period. So what does all of this mean? Well, it shows that given just a few basic parameters, we can predict the motion of an object in constant motion. We may not be able to account for all of the forces acting on this object, but if there's no net force acting on the object, then we know it will have constant velocity, and then we can predict its position with relative accuracy. Finally, I would like to answer what would happen if the axes were changed, as in x plus became x minus. Well, not much would change at all. The graph would have a negative slope as the position data would be in a negative direction, but we would still see the same magnitude of the velocity for the ball. And that's about it. See ya.